All right, thanks a lot for that intro, Jeff. And so as Jeff said, definitely the most significant addition to C++ 26 is of course reflection. Indeed, probably the most significant contribution to the language in many standards. And the reason that a lot of us are really excited about reflection is how many problems it permits you to solve in a better way than we could before. And it's a pretty long list. We can do formatting, we can do serialization, we can do structured arrays. I gave a whole talk about this at CPPCon last year. We can write a more ergonomic command line argument parser. We can do foreign language bindings automatically. We can do hashing, of course, enum to string. We can finally do. And it's a very long list of things. This is hardly by no means exhaustive. But if you look at this list, it's kind of interesting because everything on this list are things we could already do today. Like you could write all of these things by hand, but we don't want to write these things by hand. We really want to write code that writes code for us. And we don't want to do this because we think it's cool or it makes us feel elite, although that is also true. We want to do this because it's extremely practical for just general software engineering. So let me give a kind of a simple example. Let's say I have some configuration type. Maybe for now it has just some string and int in it. And this is important for getting my application started. Like I need this information. And so one of the things I might want to have is I want to print this config. All right? I want to make sure that my application is configured properly. I want to be able to look historically at my logs and make sure that what it was running with on a particular day. And of course I can write that formatter. Like this is a pretty straightforward pattern to learn. It's not a lot of code. The code is not very complicated. It's pretty easy to teach someone if they've never seen it before. AI tooling, I'm sure, can produce this pretty reliably.
Actually not.
No?
No,
Not yet?
I find it's terrible at it.
All right, well, someday. But the problem with this code is not anything about its length or complexity per se. It's the fact that it has to even exist at all. Because types like this config type, they tend to change a lot over the lifetime of an application. And so what happens if I add a new member to config? It's very easy for me to forget to update my formatter, to forget to update my YAML serializer, or whatever other utilities I built on top of config, and everything will still compile and work, and now I just have an incomplete representation of my application. And that's not great. All of this code just gives me more maintenance burden. And the nice thing about reflection is that now I can slap this annotation on top of config, and somewhere there will be one specialization of formatter that looks for this annotation and just does the default member-wise thing, and I don't have to write any code. And in fact, I can remove all of my formatters that just do this, and this is a much better place to be. I have a lot less incidental code in my code base. And I think ultimately this leads to what I think would be a good future guideline, which is no raw code. And so what I mean by this, in the same way that when Sean Parent says no raw loops, he does not mean never under any circumstances write a loop. That's not the goal. What he means, of course, is when you're writing a loop, you should recognize whether what you're really doing is writing an algorithm and use the algorithm that you're actually doing for the job. And in the same way, I think what we should strive to move toward as a language is that when we're writing code like these formatters, these serializers, this stuff that really should be generated from code that exists, is to be able to do that. Is to recognize this is just incidental code. This is not important to the business logic. Let me generate that stuff. But of course, we're not there yet. This is some future that we should strive for. We don't have the language facilities to generate all the kinds of code that we want to be able to generate. And so what I wanted to talk about today is, well, how do we get to this future? Like, how do we get to these flying cars? And in order to understand, I think, what our next steps could be, I think we need to take many steps backward and understand, like, well, how did we get to today? And what are the issues that we have today with the code generation facilities that we have available to us? And so we can learn from the mistakes of the past and kind of make the right steps going forward. And so we start with, of course, with C preprocessor macros. And C preprocessor macros, they get a really bad rap, I think, in the community, and that's because they're really bad. and of course, the biggest problem with C macros is that they don't respect scoping at all. And so, of course, you never have any idea whether some code that you wrote is invoking a macro or not. And that's pretty bad, and people guard against this. And of course, this is why all the standard library implementations use those ugly identifiers all over the place. And that's pretty bad. Another bad aspect to them is that they don't understand language semantics. And so what I mean is the C preprocessor runs before template instantiation, and it doesn't understand, of course, anything about templates. And it's a really big problem when you start using template arguments. It's like, okay, but I meant to only have one argument, but the C macro thinks I'm passing it 2 or 3 or something, and this is something you have to guard against. And these are, of course, very bad things from the purposes of a language facility. But even if you set these apart, C macros are still an extremely underwhelming feature because they don't have any control flow, right? How do you write an if in a macro? Of course, you can conditionally define a macro, but within the definition of a macro, you can't condition on things, you can't loop, you can't do any pattern matching or recursion, none of this control flow that we think of as day one things when you're learning a new programming language, maybe week one at the latest. These don't exist in the C preprocessor. And so if someone came up to you and told you that they were a Rust expert, but they didn't know how to write a for loop, you would be highly skeptical of their claims of expertise. But if someone came up to you and told you that they were a C expert, but they didn't know how to approximate a for loop in a C macro, I mean, you'd be like, yeah, I mean, me neither. Like, I don't know. This is this like very niche set of wizardry that a few people know how to do. But nevertheless, it's really useful because it turns out control flow is very handy when writing programs. And so we have this macro in our code base that, of course, the name is much longer than this to avoid some other problems. And it has this excessive parenthesization to avoid one of the other problem. And this is our way of trying to achieve that no-rot code guideline. And what this macro does for us is it's going to generate the members. And you can see that the initializer is conditional. At the end there, it's also going to generate a function that lets us iterate over all the members, or approximately before reflection. It also generates a hook that'll help build a formatter for this type. And so if you think about what this macro is doing, and there's a ton of other functionality that it generates for us, every transformation here is very straightforward. Like it's just like looping over all the members and doing some very basic transformation. But this macro is incredibly complicated. It's very difficult to write. And plus, when you make a mistake, so for instance, if I wrote sring instead of string, which for some reason is a very common typo I make, the compiler very helpfully gives me the full preprocessor expansion stack, which is thousands of lines of error that has nothing to do with the typo I make. So it's a pretty bad usage experience too. But nevertheless, it's useful, so we use it. And so like, this might shock you, but I'm hardly the first person to observe that C macros are maybe not the best language feature. And I wanted to share this quote that I found from Guy Steele and Richard Gabriel, who are some of the Lisp guys, and what they wrote in the second edition of the History of Programming Languages, now over 30 years ago, in a section talking about the history of Lisp macros and the kinds of design changes, design decisions that they had to make, was by comparison to Lisp macros, the C preprocessor is completely anemic. The macro language consists entirely of substitution and token concatenation. And Lisp users find this laughable. Why settle for anything less than the full programming language itself? Which is a great question to ask, and this is one that I'm going to keep coming back to today. Right? Because of course C does have control flow, but the preprocessor doesn't. And of course we moved on from the C preprocessor. When people were working on the problem of how do you parameterize types in C++, originally people used macros for this. This is the original implementation of standard vector from Cfront. This header actually predates my birth by a few weeks. And it's kind of interesting to look at because this also predates things like const in C++, it predates namespaces. And a lot of people realized at the time that macros are maybe not a good way of parameterizing types. And that's where class templates come from with the syntax that we're all familiar with. And class templates were designed to solve the problem of how do you parameterize types. And they're obviously much better at that problem than macros are. But there's still a lot of things that they don't do, right? We still don't have any kind of if or for. We kind of sort of have pattern matching and recursion, but just at the top level for templates, nothing in the body. And of course, we don't have like the equivalent of functions, like how do I group declarations together? And it's not surprising that class templates don't have this functionality because they weren't designed to solve the problem of being a general purpose code generation facility. But as we all know, life finds a way. And control flow is really useful, so people came up with a way to approximate it. And of course, enable if is a class template that we're all pretty familiar with. It has largely become obsolete in C++20 for the purposes of SUNE, but this is still the way in C++ to have a conditional member. And if you think about it, this is a very strange way to write if. I mean, it has if in the name, so we can kind of see it, it's like that's what it's doing. But this is not how we write conditionals in every other part of the language. Of course, how do you do loops? Tuple is a pretty simple type. For every type in the template argument list, we have a member of that type. So how do you implement tuple? Maybe someday we'll actually be able to have a member pack like this, but that doesn't exist yet. We can expand a pack in the base class list, but this isn't the right way to solve this problem because, well, first of all, we can't have multiple base classes of the same type, and then we can't have base classes that are scalar types or pointers or references or anything like that. So instead, you have to, of course, write something like this. And as far as I know, this is probably like the best way to implement tuple, at least before reflection, which is you have some meta function to generate this list of base classes that you ultimately want to inherit from. But I can't just inherit from that list, so I need this helper in the middle to unpack that stuff for me. And this is a very strange way to write a loop. Like, where is the loop in this code? You just have to know that it exists. And Boost MP11 is great, but this isn't really the way that I want to think about things when I'm coding. And so eventually we get to reflection. But the reflection that we ended up at, the one that we have today, it wasn't always obvious that this was where we would end up. And of course, when we started down this path of adding reflection to C++, template metaprogramming was the way that we solved problems. And so it was kind of the obvious choice to build reflection on top of that. The original static reflection paper had as its design that we had a reflection operator that would give you a unique type, and then you would template metaprogram around that. We would provide a library with a bunch of meta functions, and you would do the thing that you're used to doing. This was familiar to everybody, and so it seemed like the logical way to go. And David van der Voorde hopped in and wrote this paper that instead of doing template metaprogramming, we should reflect through values. And in his intro, he wrote the sentence that let's design with modern C++ in mind and leave the template metaprogramming shackles of the past behind. And it rhymes, so you know it's a true statement. And this kicked off a long series of discussions where we started talking about, like, well, what is actually the design space of metaprogramming and reflection to begin with? This was with Louis Dion. And so we talk about, like, okay, do we go with the type-based approach? Do we go with the value-based approach? And then even within this idea of, like, should we use values? It's like, should the reflection operator always return the same type? Should we return a different type based on the kind of thing that you're reflecting? This was a long series of discussions that ultimately center around this idea that we should metaprogram by design, not by accident. Right? We should really think consciously about how we want this feature to work so that people can use it. Which ultimately led to P1240, which is the scalable reflection paper, which laid out this vision of we're going to have a single type meta info that all reflections are going to return. And that is the precursor to P2996, which is eventually the reflection design that we adopted for C++26. And this was a long path. Like, some of these papers are separated by many years. This is a long series of discussions, and there are good reasons to have wanted to do something else than what we ended up with. And so it's worth asking, like, okay, well, did we do the right thing? Like, did we end up in the right spot? And I wanted to share an example here. And so one of the things that we can do with reflection that we couldn't do before is we can write our own type traits. Type traits used to be largely the purview of the compiler, because it's the only one that had access to all your class internals. And so if you wanted to write a new type trait, you'd have to implement it in the compiler, and reflection lets you just write it yourself. And so one of the traits that we have had since C++20 is this notion of a structural type. So this is the kinds of types that you can use as constant template parameters. So what used to be called non-type template parameters. And this is the definition of that term. And we didn't used to have a type trait for this. We will in C++26 now. But I needed a type trait for this for some reflection work I was doing. And so how do you implement this type trait in C++26? And now I should note that, like, okay, this word literal right here, we're actually going to pretend it doesn't exist because I can't actually check that, but also it's not important to check anyway. So we're just going to, it doesn't, whatever. Okay, and so my C++26 implementation looks like this. And so I'll walk you through the implementation because it's actually a very simple, just direct translation of the core language wording, right? So a type is structural if it's a scalar type, or it's an L-value reference type, or it's a class type. And now here there's a little bit of a footnote in that when the core language talks about class types, it includes unions. And if it wants to exclude unions, it talks about a non-union class type. But in the standard library, we have the type trait is class that is a non-union class. And so if you want to include both, you have to do it this way. So that's a little awkward, but that's actually the most awkward thing in this whole implementation. So if it's a class type with the following properties, and now we look at all the base classes and non-static data members. So those two things combined are the sub-objects of a type. And now both sub-bullets here refer to all of the sub-objects, so I'm going to handle them in the same way. And because we're looking at a property that all of the sub-objects share, I'm first going to use ranges olive. I'm going to use an algorithm for this. And now, so for sub-objects specifically, that algorithm has a precondition. I can only call sub-objects on reflections that represent a class type. I can't ask for the sub-objects of a reflection representing int. Int doesn't have sub-objects. But that's okay. I'm already guarding against that, right? The call to sub-objects of will only be actually evaluated if the type is actually a class type or union type. So I've checked that box. And so for every sub-object, I'm checking to see if it's public and non-mutable, and that the type is structural once I remove all the array extents. So this is a pretty literal translation of the code. This was very easy for me to write. It only took me a couple minutes, and the only issues I had were typos that I made along the way. And the reason that it's easy to produce is that this is just C++ code. It's regular, normal C++ code. I'm traversing a data structure that happens to deal with reflection, but that's kind of incidental, right? I can use my same ranges algorithms to traverse this data in the same way that I could deal with any kind of tree or vector or map or whatever. And of course, I don't have to use ranges. You can use whatever ranges library you want. You can not use any ranges library and just write raw loops if you want. There's no prescriptive way that you have to write reflection code. You just write it in the way that fits your code base. It's just normal C++ code that just happens to be dealing with reflections. On the other hand, in a type-based approach where I'm doing metaprogramming, the solution looks very different. And this is maybe one way that I'll implement is structural as a type trait. And so here, one of the things we have to worry about is get sub-objects. Now, this is a meta function and it has a precondition that you can't instantiate it with a reflection that doesn't respond to class type. And so I guard against that by guarding that whole specialization. Right? So instead of having these simple Boolean conditions, now I have different specializations. And now this is code that like a lot of us are kind of familiar with looking at stuff like this, but if you step back and think about it, like this is a disjunction, right? Where's my, like, how can you tell that this is a disjunction and that these are my main categories, right? The scalar L-value reference and class type cases are handled there. And you just kind of have to know that that's what this means. And you also have to just know that this is complete, and I really don't intend there to be any other specializations of a structural. But it's a very different way of thinking. It's like step one is figure out how to solve the problem, and step two, try to figure out how to fit that solution into the box that we can use. And I'm using Boost MP11 here, which is a great library, and I like it a lot, but it's another thing that you have to learn. And so a different approach to implementing this as a function might look like this, and maybe this is a little more concise, and people might prefer this. But one of the problems here is, so I'm using MP for each here as my algorithm. And I'm using MP for each because in Boost MP11, the only algorithm available that takes a lambda, which is what I need to be able to do recursion, is for each. There's no all of that takes a lambda. But what I want is an all of. Right? That's the algorithm. I'm checking to make sure that all of the sub-objects meet some criteria, but I don't have that algorithm available to me, so I'm approximating it with a different algorithm. And I can do that, and this works, and it gives me the right answer, but it's not, it doesn't bring me joy. And so if we compare these models, like the template metaprogramming world to the reflection world, they're pretty different. Right? In the template metaprogramming world, we're used to, we deal with specializations, partial specializations, explicit specializations. But with reflection programming, the way we write conditions is with if or and. And with template metaprogramming, we have to be careful about deferring instantiation of meta functions because they might have preconditions. But with reflection, we just have to defer evaluation. And differing evaluation is a lot easier because we can use conditionals. Ultimately, the main issue with template metaprogramming is you have to use metaprogramming libraries. And there are a lot of good ones, and they exist, and they're very useful. But it's this totally new thing with this that only exists to solve this one problem for this domain. Whereas with reflection, I can use the same algorithms and data structures that I use to solve other problems. And I don't need to learn a whole new set of things. I need to learn the reflection bits, but I don't need a different model of programming. So to borrow from Steele and Gabriel, template metaprogramming is kind of like an anemic functional sublanguage. And like, I have nothing against functional programming. Functional programming is great. But if you compare what functional programming for templates looks like in C++ to like Haskell, we lack all of the language facilities that make functional programming nice in Haskell. And in comparison, reflection programming can just use most of C++. I mean, it'd be better if we could use all of C++. But every standard, the amount of that most is covering is increasing, and that'll continue to increase. And it's unlikely that we're going to just like add a whole bunch of functional language stuff to help the TMP world. Because ultimately, template metaprogramming is discovered. Right? Class templates were not designed to solve this problem. Whereas with reflection, they were. We really thought about all of this stuff in mind, because reflection programming really is just regular programming that happens to operate with reflections. And that makes it a lot easier to deal with. And so now we're caught up to today, and so this begs the question of like, well, what should source code generation look like in C++? And so by now, I think I've conveyed at least my high order bit, which is whatever shape this takes, we should be able to use C++ in it. It should not be a new sublanguage that we have to learn with some new domain, with some limitations. I want to be able to generate my code in the same way that I generate anything else. And so I thought the best way to start determining an answer to this question is to turn to some programming language luminaries. Of course, the Russian composer Igor Stravinsky is apocryphally quoted as saying that a good composer does not imitate, he steals. And the great humorist and mathematician Tom Lehrer, who wrote this great song about Lobachevsky, who encouraged us to plagiarize. Only be sure always to call please research. And so if you've never heard the song, I highly recommend checking it out. Lehrer is hilarious. And so what I mean by this, of course, is we should look at our peers. We should look at what they're doing. C++ is hardly the first language to have ever thought about what source code generation should look like. Other languages solve this problem. I brought up Lisp earlier. Now, of course, Lisp is very different from C++ in every conceivable way. So I'm not sure that there's a lot that we can learn from Lisp for this particular problem. But there are two languages that I do want to look at. And these are two languages that are newer than C++. They were definitely influenced by C++, particularly maybe our mistakes. They're well-designed languages. They're well regarded by their communities. And I'm talking, of course, about Swift and Rust. And so I'm gonna warn you now that I'm gonna actually spend a fairly healthy amount of time talking about these two languages for the remainder of this talk. I'm gonna show a lot of code that is both Swift and Rust code. And it's okay if you don't know either language. The goal here is not to become a Swift or Rust expert, but rather to understand what their approach is to this problem and what we can learn from it. And so at a high level, these two languages do have a lot of things in common, even though they're designed by different groups of people to solve different problems. So at a high level, they're both definition checked. And so when you write a template in either language, or what we would call a template, if that template compiles, that template is going to work for all instantiations, which is a really nice property to have. This isn't strictly related to the question of source code generation, but I think it's a good thing to keep in mind as we talk about a lot of the other intricacies of the two. So for source code generation, both of them use macro systems. Rust actually has two different macro systems, and we'll talk about both. Importantly, in both cases, the macro invocation is visually distinct. You always know when you're looking at either Swift or Rust code that you're invoking a macro. It's very clearly visible. And both languages also have two different forms of macros. They have one that is in an expression or declaration context that injects one of those two things. And they have one that I would call like a decorator form. So similar to Python decorators is attached to a function. So they have a form that is something like a C++ attribute or annotation. It's attached to an existing declaration. And so a simple example in Rust might be if I take the same config type I had before, I have this attribute derived debug, which makes this type printable in that default memberized way. And when I go to print it, println right here is also a macro, which you can tell with the trailing exclamation point. In Swift, we have something similar. We have @debug here is also a macro. And you can also see that @main is a language feature. And so the macros that Swift has and language features, they have the same syntax. So these things really look and feel like the rest of the language. And hash line here is also an invocation of a macro. But what does this actually do? Let's go into like a lot of detail about how derived debug actually works. Like how do I actually get printing out of here? And so what this literally does is we're going to look up a function that implements this macro, and we're going to pass the tokens that it's attached to. So literally, those tokens are passed into this function. We're not doing any semantic analysis or anything like that. And the job of this function is to produce these other tokens that then get injected. Now, in a real implementation of derived debug, this is not actually the implementation that gets produced, but this is the one that we're going to walk through because I think it's a little bit easier and arguably more interesting. One other thing to note is that this is purely on a token layer. And so if config happened to be a generic type instead, all of those tokens are also passed in. So the macro operates on the template itself, not on any particular instantiation of it, which is kind of interesting to think about from a C++ perspective, where our templates are barely parsable to begin with. But in Rust, this is just how you do things. So you just get tokens in, tokens out. And so the implementation of this macro, so we just take a token stream as input, and the first thing we're going to do is we're going to parse it. And this is going to give us a syntax tree of the contents of this struct. And what we're going to do with that struct is we want to pull out the fields, right? We need to generate a call to .field for every non-static data member that we have. And this parse function gives us the whole syntax tree that we have to walk, which in Rust, the way you would do this is because these are all language variants, we use pattern matching, which is really nice. In a real implementation, I would obviously want to handle all of the cases, but for the purpose of this talk, we're just going to handle the easy case where I just have a struct with named members, and I want to pull out the fields. And now for every field, I need to generate this call. And so this quote bang right here, this is just generating a bit of syntax, specifically something that looks like this. Now, in the abstract, this is not a valid Rust expression. Like dot field or whatever, you can't start an expression like that. But that's okay. We're not syntax checking anything yet. These are just tokens. And the way that we do this is because fields is a range, we iterate over the range and we do a map, which is in a C++ world would be a views transform. So this is lazily building up a range of all of these calls to dot field, but just tokens, right? We're just dealing in token world. And once I have these calls, I can put together the full set of tokens that I need for hash name is interpolating the actual name of our type as an identifier. I'm stringifying it to get that string. And Rust has this nice syntax for doing a range-based interpolation, and that'll be all of our calls to that field. And even at this point, we're still not doing any syntax checking. Like even I have this full set of tokens right here, and the syntax is not going to be checked until this macro is actually invoked, and it is injected into where the compiler needs to start slurping up the next tokens, and only then is it going to be syntax checked and parsed and so forth. Which is maybe a little bit surprising, right? Like Rust is fully definition checked, and here we're not checking anything. We're just building up with tokens. But that's the way the system works there. And so if we compare these two right now, and I change my annotation to look more like Rust, like these look very similar from a syntax perspective, and both kind of achieve that goal of no raw code, right? Like I'm not writing this formatter because I don't need to. And that's pretty nice. But they achieve this in wildly different ways, right? So in C++, we have a reflection of config as input. The compiler is fully parsing and analyzing our type, and then it's passing, and then we have access to a reflection representing this type in the implementation of our annotation. But in Rust, we're just doing token parsing all the way. And so like I can see that the type of name is string, but I don't know anything about string. I can't ask anything about the properties of that type, and I can't make decisions based on that front. But the real interesting difference between the two is that in C++, the way I would implement this formatting right now is I have a specialization of formatter that checks for the presence of this annotation. So it's a pull model, right? I'm looking for this thing. Whereas the derive attribute directly is pushing the implementation of debug of the formatter into the code base. And so these mostly mean the same thing. These mostly both just work, except when they don't. And when they mean a different thing is, imagine now there's a different specialization of formatter that happens to also match config. So for instance, in the standard library, there's this partial specialization of formatter that matches ranges. So if my config type happened to be a range that has this annotation, now I have two partial specializations of formatter. Which one wins? Well, they're just going to be ambiguous, and there's nothing you can do about it. And the only options are either a config has to take steps to make the other specializations not match, or all the other specializations of formatter have to be aware of this annotation and reject it. So it's not quite a complete solution. So like we really do want to move into the push-based model, at least for examples like this, because it's really obvious what the user intent was here, right? Like I wrote this annotation because I want this formatter. I don't care about anything else that happens to match. So let's look at Swift. In Swift, the logic is actually quite similar. We similarly find this macro called debug that's going to do this implementation for us. In the Swift case, instead of just passing the raw tokens into this function, we're actually passing the syntax tree itself. Now, I don't know how to represent a syntax tree, so here's every tree emoji that I could find. So you get that as input. But the job of this function is to return a bit of syntax. And in this particular case, it actually can be a range of an array of syntax, and you can see that the syntax is actually kind of constructed from a string, which is kind of interesting. And this is how you opt into printability in Swift, at least as far as I know. So on the Swift side, I actually need to declare this macro now and talk about the kinds of things that it is allowed to do, which is maybe not super interesting for the purposes of this talk. But here's how I implement that macro in Swift. So I have to implement the extension macro protocol, because that's the kind of thing that I'm doing. And I have to implement this function, which is very daunting. And to be honest, I don't even know what most of these parameters mean. But this is the only one that I happen to care about, which is this is the declaration of the thing that I'm attached to, and I get the syntax of it. So in the same way that in Rust we were dealing with just the syntax, that's what I have from this type. And so from the declaration, I need to pull out all the members again. So just like in Rust, I'm only going to deal with the simple case. I'm going to require it to actually be a declaration of a struct. And now I'm going to walk through all the members of that struct. And now at this point, this is just another bit of data, right? It's just another data structure that I'm iterating, that I'm pulling out pieces of. And this is just regular Swift code with doing regular ranges stuff. So compact map is a version of transform that returns an optional and just only preserves the ones that are non-nil. And so at this point, I'm just going to walk through. I only care about the variables because I'm skipping all the functions. And it turns out that there's a lot of different ways to declare variables in a type. So again, for the purposes of simplicity, I'm going to skip the cases that like, okay, you declare multiple of them in one line, or I don't care about the computed properties, or this case was a structure binding like syntax. Of course, these cases are handleable. Because we're just doing data structure manipulation. We happen to be dealing in a domain where ultimately we're talking about syntax and we're producing syntax, but this is just regular Swift code to walk through a data structure. And ultimately, store properties ends up being just an array of string, right? And specifically these strings. I've successfully pulled out the names of my members, and now I need to turn those names into, again, the little bit of Swift syntax that will actually interpolate the values that I need to produce. And so, for instance, I need to produce something like that. And of course, Swift being a modern language has nice facilities to deal with strings. And so doing things like joining a string with a comma is like a nice and easy thing to do, unlike some other languages that I'm familiar with. and once I have these pieces, I just go ahead and I produce the ultimate syntax that I need to inject. And so just like Rust, all I'm doing here is I'm building up the string of syntax that I'm producing, and so none of this can be checked, right? There's nothing here for the compiler to check at the point of definition time. I'm just dealing with strings. The compilers only check that the syntax is correct when I actually go ahead and do the full injection. So this try extension decal syntax bit is like, this is the kind of syntax that I'm constructing, and that constructor there at that point can actually check the syntax, but it can't check anything like the names and stuff, right? Like if I accidentally got some of the names wrong, it's not going to catch it there anyway. So this is ultimately we're just producing a string to inject at this point.
So just like in C macros, so if you want more complicated strings, then you have to remember to put parentheses around it and like escape arguments and stuff.
So unlike C macros though, this is Swift code, right? This is, I can do whatever I want in Swift to produce whatever strings I need to do. And so it is certainly unlike C macros in that sense. But yeah, like if there are things in which parenthesization matters, like yeah, you would need to produce parenthesization because this is literally the code that you're producing in the end. And so if I compare these two,
Barry, I'm sorry. While we're on,
yeah,
a few questions about that.
Yeah.
So, in a sense, this is like taking. Granted, it's in the language that you're going to be using at the end, but maybe I wrote a Python script that did some code gen and it globbed a bunch of strings together, and now I've got a thing that I'm going to be working on. That I think what you're calling the push pattern definitely has a variety of different problems from pull. What do you see are the advantages though? The one, obviously, the syntax checking is late. That gives us some advantages, but what are there downsides?
So when I think that's like two separate questions, right?
Okay.
So the advantage of push is that I can reliably get the customization that I want, as opposed to pull where you have to deal with just like multiple possible specializations, and of course like we don't have like a real language customization mechanism in C++, so we inherently have this problem. But the separate part is like how do you produce syntax is I think separate from the push-pull question.
Okay. You can continue.
Okay. So if I compare these two, you can see they're actually surprisingly similar in the way that these two macro systems work. Versus in Swift, I have this function that takes some AST and is supposed to produce an AST, but arguably it's also fair to say that it just produces some string for the code that we're injecting. Rust is maybe more direct in that sense. We're just taking tokens and we're producing tokens. Of course, we go through an AST on the way to get there because we probably need to do some parsing. But ultimately, we're just dealing at the token layer. In both cases, these macros are purely additive. We're not mutating any existing code, although Rust has other kinds of macros which do allow for that kind of mutation. In Swift, you actually have to declare what your macro is going to inject, which seems kind of nice from the tooling perspective, is you don't know what specifically the contents of the macro are going to be, but you know what names are going to end up there. Versus Rust is more like anything goes. But ultimately, like we do get late checking only for all these cases. We're just producing syntax. When we finally go to parse that syntax, that's when we go to check these two things. And so because we're just doing string to string in Swift or tokens to tokens in Rust, these things are actually very easy to test, right? Because you just test that you got the output that you expected, which is pretty nice. And so like, what do we, if we step back and have a think about this, like, what do we think about this for C++? Now, this token or string or AST-based input model, that probably doesn't work for us as a language. You know, we're like, Rust and Swift are parsable, which is obviously a big advantage, versus C++ is maybe not. So this approach of just passing in like raw tokens of the whole class template is unlikely to pan out for us. But we have reflection already, and that's probably the way that we want to lean into this, is to actually rely on the compiler to parse this stuff for us and give us a reflection in. But on the output side, I find the raw syntax approach to be pretty appealing. It's certainly a pretty interesting one to think about, and I want to go through like a few examples. And I'm going to not talk about formatting for a few minutes of my life, and I'm going to instead talk about tuplecat. All right, this is an algorithm that we've had in the standard library for a while. This is the complete specification of it. And if you look at it, it looks like super daunting as a specification. We're introducing 8 different variables. We have both superscript and subscript going on in this definition. But like ultimately, tuplecat is not a very complicated algorithm. Ultimately, we're producing some specialization of tuple, where the types come from the tuple elements of each of our arguments, going down the list in order, and the expressions correspondingly come from calls to get. So if I walk through kind of a simple example, let's say I have a one tuple, a pair, and an array, which are our three kind of tuple-like types. We need to produce some kind of tuple, and the first argument is going to give us one type and one expression. The second argument is going to give us those two types, and for the array, we're just going to get d 3 times and those three expressions. Of course, the expressions are actually going to be calls to get, but I think this is a little bit easier to reason about. And so note that we're preserving the reference from C, but the other ones are not reference types because those are the actual element types of those tuples. And so you can think about, it's like, okay, well, what is this algorithm? Well, we're going to walk over every argument, and then for each argument, we're going to walk over the elements of that tuple, and that's how we build up this structure. But how do you actually implement that? Like, that's the algorithm. But step 2 is like, okay, but how do I conform this algorithm to a way that actually works? And so the best way I know of how to implement tuplecat, at least in the C++ we have, which I think Peter Dimov came up with this approach, is so you start by numbering your arguments. For each argument, you produce the sequence of indices into that particular argument. Then you extend the upper list to be the same length as the bottom list. And what you end up is 2 lists of the same length. And in this particular case, we have 2 lists of size 6, 2 lists of integers, and that is the size of the resulting tuple, right? I'm producing a 6 tuple, sextuple, 6 tuple. And what having these 2 lists together give me is a way to do a single pack expansion to produce the resulting tuple, right? Because we don't have iteration, we have pack expansion. And if we want to avoid kind of piecewise putting together tuples one at a time and minimize the amount of copies and moves we have to do, we really want to produce the whole result in one go. And so we can do that. We can write a meta function to turn a tuple into a list of its corresponding types, which of course, again with MP11, we really want to live in a type-based world, and even though tuple element t exists in the standard, it takes an int, and we need it to take type, so we kind of have to wrap that. And then we can do a bunch of metaprogramming to produce the tuple number list, which is our inner list, and we can do a bunch more metaprogramming to produce the outer list. And like you can do this, and I had mentioned that I like MP11, it's a good library, and it makes this as easy as possible, I guess. And with C++26 now, we even don't need inner and outer to be type lists anymore. We can actually unpack them and use packs and structured bindings and make them context first, so that inner and outer are now actually those lists of integers that we want. And so then ultimately we can produce our tuple in one go. And so this is kind of nice. We can actually finally implement tuplecat in one function template without any indirection. Of course, I needed those 3 other alias templates out front because I needed more work, and we can't have local alias templates. And you know, this doesn't really resemble the original algorithm I talked about in terms of like walking through the arguments and then walking through the elements of those arguments, but it works. This is certainly a solution. But what could it look like if we actually could just put together the pieces that we need to put together? And so, you know, let's kind of borrow this Rust idea of having just raw sequences of tokens. What we can do is we can start by, we have an array of our reflections of all the types of our arguments, and we're going to build up two vectors, the vector of C types and the vector of the expressions that we need to produce. So C types and C elements are the names that the spec happen to use. Types can just be reflections representing types, and elements are going to be our token sequences. These are the expressions that I want to put there. And so I'm gonna have my 2 nested loops, right? I'm going to loop over the parameters to tuplecat, and then for each parameter, I'm going to loop over the number of elements. The next type is just the kth tuple element of that type. And now maybe the next element is going to be this expression, right? I need some call to std_get with an appropriate value on the appropriate tuple, and so this might produce the token sequence, something like that. I'm interpolating k and I here to produce my token sequence.
Can I ask what this is backslash?
So backslash is, we need an interpolation syntax. So Rust uses hash for that. We obviously could not possibly use hash because the preprocessor claims it. And so one of the issues in this world is like, well, you need some syntax to do interpolation, and that syntax cannot clash with anything that is valid C++, because we want to be able to inject anything that is valid C++, which sort of limits the syntax options available to us. backslash happens to be available, so that's something that we could do.
But to make it clear, this token sequence stuff is proposed. It's not actually in C++26.
Right, this is not in C++26. For that matter, it may not ever be in any C++. So this is we're just doing a thought experiment here of what it might look like. But this is the expression that we want to write in our code. Right? Like we want to produce this sequence of expressions, these calls to gets with the right indices. And once we have these two things, well, we have substitute already to produce the actual return type of our tuple. That is in C++26. And we need to join all these expressions with a comma. That is not in C++26. But once we have this, we just need to inject this right return statement for us, right? Because we're just returning this particular tuple with this set of expressions. And so if you compare this to the previous implementation, there's obviously some new stuff here, like what is this token sequence stuff? What is this new syntax for interpolation? But I like this approach a lot better. And I don't like it because it's shorter. It is shorter, but the fact that it's shorter is really a consequence of the real reason that I like it, is that it's simpler. I can just write regular C++. I know what algorithm I want to have to produce the result, and I just do that. So it's a much simpler model to deal with. And the consequence of just being able to write regular C++ is that I can just do this, right? We don't have any way to iteratively build up things in a template metaprogramming world. And even once we get into this frame, then we can talk about things like, well, why did you write like a regular for loop? Shouldn't that be enumerate? And yeah, probably should be enumerate. And we can talk about like much more interesting things than like, well, what are all these MP11 algorithms that you're using? What is even going on? Is this even possible to understand or debug? Yeah.
If you're going to do this, why wouldn't you just go all Rust and just return a vector of tokens? If you build it up fully, put the return and everything else on it, and that would be a return type, and let the compiler sort of deal with that.
Yeah, so that's kind of what I'm doing here. So Q injection is just a function that takes the token sequence. So instead of having like a function that returns them, I'm actually passing it through to something else. I think that's just a question of like, well, what is the actual shape of this thing needs to look like? But the model is definitely the same thing. Okay. It's just like, here are these tokens. This is what I want you to put in at this close brace, and the compiler just does that for me. Yeah, Ben?
The token injection, is it automatically splicing R extras?
Yeah, so in the way I'm thinking about it, because R is a reflection representing a type, and of course the compiler knows that. And so what you want here all of the time is I want that type. So what I want is just give me like a pseudo token, like a fake token, and what it is it represents that type. Like, don't make me spell it out. You know what it is already.
But it's not splicing K above.
It's not splicing K. So K is just an integer, and so what I get is that value.
There's no case where you would want it not to splice R?
Well, if you want it not to splice R, there is a case when you'd want that, but I think of that as being like the rare case. And so if you want to not splice R, you could just wrap R again with reflect constant. And I think in this context, like I think syntax is going to be very important, and you want the syntax to be light. So I'd rather the rare case to be like, okay, no, I really just want this to be a reflection, versus the almost all of the time, if I have a reflection representing a type or a namespace or a template, like what I want to splice is that type or namespace or template. I don't want to have to then splice it as a result. It's just like more syntactic noise. It makes it harder to understand. Yeah.
Why not just string? So for interpolation, we just use std format, and it just gets a string return, and
Right. Yeah. So that's a good question too. So of course Swift does use strings. So why not strings? And the problem with strings, I think, is I think strings have multiple problems actually. So first, I think dealing in tokens is easier for the compiler because it's going to lex them on the way in, and then it's done. With strings, it's going to have to relex the result. That's more work. The real problem with strings is like we just don't have good string facilities in the language, so that just inherently makes them harder to deal with. And our main string facility is format, which is great. But if you're using format to inject C++ code, the fact that format uses braces for interpolation means that when you want to actually write a brace, you have to escape it all the time. And so like now it suddenly stops looking like C++ code, right? You have all these double braces everywhere. It's a lot harder to deal with. It's not going to get automatically syntax highlighted for you, right? You can see that like my token sequences are highlighted for me when I paste them in, which is kind of like a nice thing. So I feel like for us, strings are just like strictly worse than having like a dedicated facility in basically all respects. Yeah.
Let me flip the question a little bit. Why are we messing with token sequences at all? Why do I care about the fact that my token sequence needs to be joined by a comma? I have a set of elements that are going to be a part of this tuple cat. We know that this is the set of elements. Why can't I just have a meta type that says this is my set of elements that I'm describing? Why do I need to retokenize it, feed it to the compiler? Like,
Yeah, can't we go with syntax trees, right?
yeah, why can't I just describe the abstract syntax tree directly or some notion of a syntax tree?
Yeah, so that gets into the question. That's I think a much larger question to talk about, and it gets into the question of like how, in order to get into a syntax tree, you have to have some notion of like, well, how do you parse this thing? And that gets into the question of like, well, C++ is very difficult to parse, and now we suddenly have to introduce all of these other types of syntax that we wanted to parse as. And so the question of like, well, what actual benefit would we get from having that extra stuff? And I'm personally skeptical that there is much here. Like it's like, yeah, like okay, this is an expression, and I want a common set of expression trees, so like we can build up like a set of syntax types to do that. But like all I want to do is like produce this sequence of expressions, and I think the token sequences kind of get there.
So the shortest path, right?
Yeah, it's just like I don't know that there's any much additional benefit to be gained, especially because just like in the Rust and Swift world, there's not much that I can check here. And C++ is actually even worse in the question of like, well, how much can you even check here? So there's not much that we're going to gain in the question of like making it easier to implement stuff.
One way to think about it is you have to standardize what are all of the tokens in C++.
I agree. Yeah.
Versus standardizing what is the syntax tree in C++. And I don't think any two compilers have the same syntax tree for C++.
Certainly it would be an abstraction across the compilers, not any one implementation. But yeah, I agree.
But it's a different idea if we just standardize string interpolation and compile time, like for at least basic syntax of C++. Can it work?
Well, the problem is like, so you have like the brace issue that I mentioned before, because like if we standardize string interpolation, like that string interpolation had better look the same as std format, because otherwise what are we even doing? That'd be very strange.
No, I'm talking about like Swift like string interpolation, where you have like placeholders with the code inside.
Yeah, I think that would be very surprising though, because then we'd have two completely different string manipulation facilities that ultimately are solving the same problem but in different contexts. I think that would be a little problematic. Yeah, Lisa?
Yeah, I look at this and like, I am all for not doing tokens in, get away from the parsing, all that. I totally understand that. What I don't understand really, apart from its expedient, is not doing the same thing on the reverse, because C++ is not only difficult to parse, it is difficult to generate. So, if I have to think about, I have reflections of, in the future, two expressions, and I want to produce their product. If I have to think about, oh, this one uses a bit shift operator, and so I need to put parentheses around it in order to get the product right, I'm going to make mistakes.
And like if you introduce variables, and you also have to care about name collisions and stuff.
So I would be, I understand that it makes everything harder to implement and maybe even harder to learn. But I've got to say, I look at languages where you generate a language that is designed for humans to write with a computer, and the first one I think of is SQL. And when you generate SQL that is designed for humans to write with a computer, you make mistakes.
All right. Well, I'm gonna keep going in the interest of time. So let's get back to the formatting example I talked about before, because I talked about how we really want to get into a push-based model instead of a pull-based model. But we have annotation, so this is I think kind of the way that we have to move forward. Like we have these things, and so one way to do that is we could say that rather than trying to introduce a model where we're actually going to pass in the tokens of config somehow or AST or whatever into this annotation, we're just going to get a callback when the type is complete, and here's a reflection representing that thing. I think this is a model for us that I think is probably more viable long term. And so so when this type is complete, we can go ahead and do something with that. And what do? Well, first we're going to require that this thing is a type, because that's the only thing that you can make printable. And at this point, we can do something similar. We can walk over our non-static data members, and we can produce that corresponding call to format to. We're putting together that string literal with dot identifier of equals braces and formatting that object. And note that out here is a variable that I haven't declared yet. That will come in a future sequence. And this list builder type is just a convenient thing, kind of to a question that you did earlier. It's like, how do I group these things in a more convenient way? I construct this thing with a delimiter because I'm introducing this extra comma space in between every token. There are several other ways to build it. This was just the first way I happened to think of. Yeah, Braden?
Are you able to compile this code that you're showing today? Do you have an implementation of this?
Yeah.
Cool.
Yeah.
Great.
And so at this point, once I build up all of my fields, where I start with declaring out, there's my original formatter, and here I need to remember to escape the brace because I'm using format, so I need that double brace. And fields is all this stuff I put together earlier. That's the calls for each field specifically. And then I just inject this into std. Right? I'm injecting this explicit specialization into a different namespace. That's a totally reasonable thing to do because namespaces are open. I can add stuff to there whenever I want. And so this is my way of actually doing push-based rather than pull-based formatting. And so avoids that question of competing specializations, because this is now an explicit specialization. I never have this problem, which is.
Thus far you've used Q injection on namespace, which is open.
Yep.
Great. And on the function being currently defined.
Yep.
What do you do for classes or structs which are closed?
So same thing. So Q injection would inject into the context in which it's at. So if I'm building up a class, I can Q inject into the class itself because I'm inside of it right now. But
debug annotation was handed the completed class.
Debug was annotation of the completed class. So it is not allowed to inject something into the class. Okay. Classes are immutable. There's a whole class of problems that I'm not talking about today, which are, well, how do you actually mutate the class that you're attached to? Because mutation is also something that we definitely cannot do in C++. We'd have to have a completely different model of things. Like the meta class model was not mutation. It's you grab this type, you hide it somewhere else, and then you produce a new type from scratch that has whatever changes you want to make. That's probably the way that we'd want to approach something like that. And so, going to a slightly different problem is, kind of the pinnacle of the code injection problem is macros, expression macros specifically. And so I find that, especially in the C++ community, because we've had such a bad experience with C macros, that people tend to overgeneralize from that and conclude that all macros are bad everywhere, which I think if people have used other programming languages that actually have good macros, people like them because it turns out the macros are useful. And Swift and Rust both have a very good expression macros. Indeed, the example for Swift, if you look at the original talk that announced them, and even if you go to Xcode and you add a new macro, this is the macro that gets added to you by default by the tooling, is stringify. So stringify takes an expression and gives you a tuple of the expression and the string version of it. This is the kind of thing that you need a macro for because a function can't do it. And if you look at the way that this macro is implemented in Swift, it's very interesting. In that it's typed. This is the declaration of stringify. It looks like a Swift function template. Indeed, this is what an equivalent function template would look like in Swift. The only real difference is that this one's declared macro and this one's declared func. The macro has this extra role at the front because it's an expression macro. And this is like a really interesting consequence. And the Swift expression macros have this look and feel of Swift functions. The arguments to this macro are actually parsed by the compiler on the way in. Everything's type checked, but it is still a macro, so you can control what the resulting expression ends up looking like. And you can do something like, so to implement stringify, I'm returning, again, the string. That's going to be this parenthesized, comma delimited, the actual argument, and then the literal of the description, which is how you do stringify. Maybe a more interesting macro in Swift is a log macro, where we want to make sure that if I don't have this particular logging level enabled, that I'm not even evaluating the argument. So in this case, if I don't have debug logging enabled, I want to make sure that f of 1 isn't even invoked, but f of 2, of course, is, and I get that nice logging. This dot syntax is unrelated to macros. It's just a nice Swift mechanism to pass enums as arguments. Zig has something similar. It's a pretty cool syntax. And so again, the log macro is typed. It takes a level and a string. And the implementation is going to wrap that message in a lambda. It's in a closure. So we've kind of achieved that lazy evaluation. It takes a lot of work to get to that laziness, but we've got there. And note that in the implementation here, we just have like these AST nodes that are our expressions. We don't have the types. We don't have the names of the arguments or anything like that. Of course, with logging, you probably want more information than this. You probably also want to add file and line information, which are other macro invocations, but we just inject the string that is that macro invocation, and then when that injection happens, those macros get evaluated as you might expect. And so when I add that, I can get also the function and line of my log, which is nice. Now, one of the consequences of this model that Swift has, where expression arguments have to be parsed, have to be part of the language, is that you can't just invent arbitrary syntax. So for instance, there's a proposal in C++ to add an implication operator. And of course, it's easy enough to implement an implies macro that is a comma b and have that lazily evaluate b only when necessary. But let's say I just really like this arrow, right? And I want the macro to have this look and feel. I can't do this in Swift because this is not a valid expression in Swift. I mean, I can actually, in Swift, I can make that a valid expression because you can define whatever operators you want and make this like only usable in the macro, and then the macro implementation just enforces that the expression has this shape. That feels kind of weird. I doubt anyone actually does this in Swift. What you could do instead is you could actually make this a string. And the implementation of the macro just parses that string and pulls out the A and B part as expressions. And because we're strings all the way, this also just works. And dealing with strings is actually, I think, pretty idiomatic in some senses. In Swift, for instance, there's this generate your boilerplate macro that takes a string of things we want to substitute into, and this is how you would generate like all of these types. Now on the positive side, there's a particularly cool Swift macro called predicate in the standard library, where of course in Swift you can write an arbitrary predicate to check things about a type. That's not particularly hard. But what if you want to do more interesting things with this resulting predicate? For instance, like I want to serialize this somewhere. I want to store this in JSON. I want to pass this to another application that's doing some kind of research. How do you write your predicate in a way that's nice and readable in code, but then also make it serializable? And what Swift does in this case, you can take advantage of the fact that this lambda will be completely type checked by the Swift compiler. We can validate that like, yeah, t.price and t.symbol exists. These checks are valid. And instead, it's going to generate something that looks like this. And this is a completely different structure that it just read through the lambda and produced something that is actually serializable, which is kind of cool. This is something that's possible. Rust is very different, on the other hand. It's a very different philosophy around expression macros, which is basically you can do whatever you want. And so the Swift approach to stringify looks kind of like this. We declare a pattern that we're matching our input tokens against, and we inject tokens that are the result of that pattern. Now, this isn't quite entirely token-based in the sense that when I'm matching an expression E, the resulting expression is that whole like syntax node that is that expression. So the kind of issues that a few people have mentioned earlier with like parenthesization and precedence, these don't come up here, right? This is the full expression. And doing something implies where I really, for some reason, insisted on having expression, arrow, expression. That's also very easy to do in Rust. I just write that pattern that I'm matching expression, arrow, expression, and I inject the correct code. And this just works. For instance, I can have an implies macro. And if A is less than or equal to 10, that just evaluates as true, and I don't panic. And now this approach to actually writing DSLs is, I think, pretty idiomatic in Rust. People do this a lot. And so, for instance, here's kind of a macro, and what this macro is doing is is it's implementing support for multiplication from one pair of types to another output. And you can see that the invocation of the macro, I'm adding these parentheses and this arrow, which makes it easy to see in the invocation like how these things are grouped. Right? It's like easy to see for the reader that like, okay, this is U8 times non-zero U8, and that produces a U16. And you could, of course, write this macro to just take 4 types, but like having this extra DSL niceties, it just makes it a little bit easier to read. Even though these are the only 3 invocations of this macro in this code base, and they're all right here, it's just a little bit nice and extra to add. Of course, you're not limited by one pattern. Macros in Rust can have multiple different patterns. Vec is probably the one that people are most familiar with, which has 2 different uses, and it even has a repetition primitive. So a lot of these things are kind of nice to produce. And so, for instance, like I can produce like a dict literal, like in Python. This is not in the Rust standard library, but I can write this. But if I really wanted to go full Python, because Python, of course, uses colons, I can't really do anything. Because Rust expressions can actually have a colon in them, and so how's the compiler going to know how to parse this? But Rust expressions can't have a fat arrow, so you can't really do anything. But it's pretty easy to produce arbitrary DSLs. One of the most interesting ones that I'm personally familiar with is from the Tokyo library, and this is like the Rust asynchronous framework that a lot of people use. And so select here is a macro that chooses one of a bunch of concurrent branches, and it picks the one that's available. And the syntax in the select invocation, like this is not valid Rust syntax, like it's completely meaningless, but it's a really expressive way of writing the code you want to write, because you pick stream1.next. If that actually evaluates to that particular pattern, if there is some value, then I go and I run that handler. And this is a nice way of doing things. Now, Rust actually has 2 macro systems that you can use for expressions. You can use the declarative ones, which I showed before, where you show the pattern or the example by which we're parsing these tokens, and there's the procedural macros. So the original debug implementation that I showed, that's a procedural macro, and in the procedural world, it just tokens in, tokens out. And so it's up to you to figure out how to parse them, like how to make sense of any of these tokens. And so in order to parse this, there's a library for that. So I can write a type. In this case, I'm looking for an expression, then the fat arrow token, then another expression. I have to implement how this thing is parsed from an arbitrary token stream. And then I go ahead and I write my function that first parses that macro into my type, and then it ultimately like injects returns the tokens that I need to inject. And I end up with something that looks the same, perhaps unsurprisingly, since I'm doing the same thing. It may maybe be more obvious if I actually use the same variable names in both cases. And so, like, what do we think about these 2 different models? I mean, it's pretty easy to look at the one on the left and be like, well, that is a lot less code. It is straight to the point. The pattern that I'm parsing is right there. It's very clearly visible. But the one on the right has a lot of advantages too. In particular, because this is just a normal Rust function, I can do whatever I need to do in it. I can do arbitrarily complicated things to build up the tokens that I need to inject. It has a lot more functionality. It's a lot more flexible. So it's not necessarily particularly obvious that like the declarative approach is the way to go. And there's a lot of reasons to really prefer to have that procedural thing as at least an option available to us. And so one cool example of something that you can do procedurally but you can't do declaratively is in the SQLX library. There's this query macro, because of course you might want to query a database. But if you look at what's going on in this example, it's like I'm running this query, I'm getting my ID, name, and email from all my users, and I'm just printing them. But I'm printing them by name, right? I'm not looking up the fields by string. These are actually identifiers. And this works because rows is actually a vec of record, which has an I64 field for the ID and string fields for the other 2. So how does this actually work? It's not like that the library is just guessing that like, oh, ID, that's probably an int, and name and email, that's probably a string. It's good enough. This macro is actually going to, at compile time, connect to your database or whatever approximates your database. It doesn't have to be the real thing. It's going to validate your query, and it's going to look up all the types for you and figure out what you need. And the result of that is if I make a typo, if I look up ID2, that's actually a compile error because there's no ID2. And so there's a lot of potential things you can do in a world where if you're not just limited to pure token substitution and token pasting, right? Like having a full function available to you just lets you do more things. And so if we compare these three, they have very different approaches to solving the problem of how do I parse the input to my macro. In Swift, we just parse expressions. So Swift macros look and feel like Swift functions. And we solve the parsing problem by like, okay, they're just functions. We're just going to reuse the same machinery there. For declarative macros, you actually provide the pattern or patterns that the compiler needs to match. And then for procedural, it's just tokens all the way down. You're on your own. In the Swift world, in the same way that we saw earlier, we produce on the output side a string or AST. In the Rust world, we're just producing tokens. In all these cases, again, we're just doing late checking. There's no actual checking of any of the syntax we're producing until injection actually occurs. And then the model of what you can actually do is very different. In Swift macros and procedural macros, the implementation, these are just regular Swift and Rust functions. And so you can do all of what's available to you in Swift and Rust code. Like however you want to produce your tokens, it's available to you. In declarative macros, it's just substitution or repetition. So in this sense, it's a lot closer to being a regular C macro. And that's very derogatory because I don't mean like they're like what C macros could be if C macros were awesome, but they're still very limited in that sense. Like you have your pattern, and you can do stuff with that pattern. We have these nice substitution repetition primitives. They have scoping. Things are grouped by AST notes. You don't have to worry about parenthesization as much. They're hygienic, right? So they have all these things that C macros don't have, but they're still limited. Right, they're still not full functions. And so the question is like, okay, so like that's what macros look like in other languages. Like, what should macros in C++ look like? And this is one where, like, to be honest, like I don't really have much of an answer. But we can walk through some examples of things that we might want to support in macros to kind of learn about what they could look like. And the easiest one to start with is, I think, forwarding. Like this is a macro that I think a lot of people have in a lot of code bases. Some people probably have multiple different versions of it in code bases because it's a very easy macro. And some people have a macro like this to avoid instantiating SID forward so things compile faster. But personally, I like it because forwarding is a unary operation. And being able to have a forwarding macro makes the code look like it's unary. But a call to SID forward is a binary operation, right? It takes a type and an expression, even though the type is derivable from the expression almost all the time. So it's kind of, it has the wrong arity. And so I like the macro approach. And so in a C++ macro world, like how might forwarding work? Well, we could go all types all the way, right? Like we have a type on the way in, sort of like a function template. And on the way out, we have an expression. And we just say like, okay, this macro gives you that expression. We're just like all types all the way. That's one approach. We could go back to token sequences and have this macro return the tokens that we need. That could work in this case. Or we can just be all tokens all the time, which in this case is very simple because we don't have to do any parsing at all because we're just consuming the entire input. So like what can we learn from forwarding? I don't think we can learn anything from forwarding. Any option basically works fine. So let's talk about assert. And like, yeah, contracts and whatever, but how do you write assert as a macro? Like it's not that big of a difference. Like we're going from forward, which takes one argument, to assert, which takes two. But it turns out this is an enormous increase in complexity because it turns out that just counting expressions is hard in C++. Like how do we make sense of this? Right? Because if you look at something like this, we have this problem of like how many expressions am I passing to call? And so if call was a C macro, the answer is just 2. We're just unconditionally passing 2 expressions. But if this is regular C++ code, the answer is it depends. Like this could be 1 expression, or this could be 2 expressions. It depends on what the types of all of these things are. And if we're going to have like a new and better macro system, like it better parse this correctly based on what the code actually is. Like this better be either 1 or 2 arguments based on like what the expressions actually are, because like otherwise like what are we even doing? Like what's the point? And so like again in a typed world, this is easy. Like I have 2 expressions, so I'm just going to declare my assert macro to take 2 expressions, and it doesn't super matter what if I'm actually returning an expression or returning a token sequence, that works. But in the token sequence all the way in, like, okay, now we suddenly need like a parsing library. We need some way to make some sense of these tokens. So we need like this whole set of abstractions for like how to pull out expressions and what kinds of things are we allowed to pull out. And maybe someone like Zach will come along and give us a library to give us some sensible syntax for parsing expression, comma expression. But this is something that we're going to need to, we would have to solve. Alternatively, we allow macros to be defined somehow so that the parameters they take are actually kinds of grammar, and we parse things that way. Like I don't know what this ends up looking like. Maybe this works. But if we look at a completely different example, so for instance, there's this library boost lambda 2, and it uses a lot of macros to define just a bunch of function objects. Right? This is pure like, we're defining a bunch of binary function objects with these operators. We're defining a bunch of unary function objects with these operators. So what might that macro look like? Well, we could do something like, okay, we're just going to define a different macro for every shape. Or we could get really cute and we could say, that, okay, like, well, what I really want to do is I want to define the macro in such a way that I'm passing an expression that looks like the use of it. Right? Like maybe that seems pretty nice, and that would be a nice way to differentiate between star x for dereference and x star y for multiplication, which otherwise would both just use star. So with a type-based model, you can't really do anything except for pass strings. So the only option is pass strings, because none of these are like valid expressions or anything like that that's parsable. That seems pretty underwhelming. I don't think we'd really want to resort to something like that. With the token sequence all the way in approach, it's like, okay, but like now I have to like do all this parsing, and this is kind of complicated. It gets a little bit nicer maybe if we like go all in on the like actually having types and differentiating that way. But this is what that approach looks like in Rust. And like on the one hand, like, okay, this isn't so bad. It's pretty nice to produce all of these different patterns. But on the other hand, this also gets pretty complicated really fast. And it's easy to suddenly have these patterns be a lot harder for users to read as they get more complicated. But of course, like with assert, like we don't just want to have like a binary assert that takes two expressions. We probably also want to add more context to this, right? We want to print some kind of string that we want to format to provide more information, so that when an assertion fails, you have more knowledge about what's going on other than just the expressions. And this is obviously very easy to do in a type-based model. You just write a variadic template. But again, this becomes much harder in a token sequence model. But on the other side, like, I have on an occasion or two complained about how verbose lambdas are in C++, especially for the easy cases, where on the one hand, it's actually super nice that lambdas have the flexibility that they have, because you can write arbitrary complicated things, and you can write very long lambdas that do whatever you want and control the capture and everything. But what we pay for that is that in the simple case where like I just want to like sort my points by x, for instance, that's a very verbose thing to write in lambdas, and it would be nice if I can just write something like very terse. And this obviously does not work in any kind of type-based macro model. But if I have token sequences, yeah, sure, like I just like walk the token sequence, I look for identifiers, I pick out the largest one, I determine the arity from that, then I produce my parameters based on that arity, and then I inject the body, which is actually like the argument into the lambda. So that seems pretty nice and easy to do. I don't know. So this of course begs the question of like, okay, like which way should we potentially think about going? Do we go with the type-based approach for the macro side? Do we go to the token-based approach? And really, this I think undersells the difficulty, because we really have like all these paths going all over the place. Some of them kind of like go out into space. Like some of these things are really shiny. Like, and I don't really know. It's a pretty difficult problem. But I think it's one that would be pretty cool to have a good solution for. Because it turns out like people still use C macros for a lot of things, because C macros are so useful. And it'd be nice to replace that with better technology that's a lot more useful to solve problems. Yeah.
At least on the input side, is it clear that we have to choose, or that we kind of say, I need something where it's beneficial, that I have a parsed thing because I need that power, or I have a thing where the token sequence is better and then I do it, I consume a token sequence.
So on the one hand, I can look at like, okay, well, if I just took a token sequence as input, that is obviously the most general solution that can obviously handle all possible inputs. But is it actually possible to like, how complicated are these things going to be to implement? How hard to understand? The type-based one is, I think, a lot easier to implement. And by implement, I mean both in the sense of like in the compiler and the user writing these things, because I think we've all written functions and function templates, so writing a type-based macro is, I think, pretty easy to understand. And so Both have a lot of benefits, and both have a lot of cost and limitation. And I don't know. I think it's an important thing to think about, but I don't have any more insight than that into this problem. Yeah.
For token sequences, because like as illustrated by the existence of type name, right? Like you need access to like the compiler symbol table to actually tell you, like you don't know if that's a template or two less than expressions, right?
Right.
Or
So
less
like
than greater than expression, unless you know.
yeah, and so like that's the thing. So like if we do do like a pure token-based input, we need to parse those things and we need to pull out an expression, and that parsing had better be correct. Like it better be contextual and understand what these things to parse them correctly. Because if it can't, then like this is a bad solution. And so like how do we actually make that work?
Wouldn't it be better off to have access to AST because that tells you how it was parsed?
Yeah, maybe. But then you also run into the problem that like someone else mentioned earlier is that like, well, not every compiler, not every C++ implementation even has an AST. Like, how do you standardize on this? What does the shape end up looking like? So like, to the extent that something is standardizable, it would have to be like very high level. Like something like expression is viable, but like going something like narrower than there, like binary operator, a cast expression, assignment expression, like I don't, like how precise do you want to be in the grammar? It becomes a much harder problem.
Well, for your example, you would have to know like whether it's a template ID or not.
Possibly. Yeah, I don't know. Yeah.
So Meta already does this though, right? Because we can already query elements of the AST. We don't call them that, but we can query things about them, their names and elements like that. And then define aggregate already goes the other way, right? We could inject things into the AST already programmatically without using tokens. So in the small, we already are doing this in C++26.
Kind of, but none of these things are like AST.
Mm-hmm.
Like we never really talk about like specific elements of syntax in any of these things, right?
We don't say it that way, but the point being we are already doing this in the small without dealing with token streams.
Yeah, kind of, yeah. Yep.
There are a lot of compile time parsing libraries that can do things like the SQL examples that you saw. Both of the Rust macros can be implemented at compile time in C++ with compile time parsing. So we can already create like an intermediate representation of some costume syntax and then use it to generate something at compile time. It's a callable object. The generation part is what is missing because we're using templates to generate the reflection and all the upcoming features. So this is, I think, where the main thing is lacking. Like the new macro system, we already have a way to do it at compile time. There are also ways to get an intermediate representation of the C++ code, but it's more tricky. When it comes to going to token stream, the main issues that I see, because let's say I want to reflect something about the body of a function. If I get the token stream and I want to parse it, then I'm like parsing C++ at compile time from a token stream is infeasible in my opinion.
But that's not. But like the compiler is already parsing C++ from a token stream, right?
Yeah.
So we do have the existence proof that it's possible. It's more the question of like how does it understand the right context? How do these things pass together? How is it possible to understand what code you're writing? So you know, it's certainly not impossible, but like how do you make it work such that it's easy to use?
Yeah,
for
parser
people?
needs the type information that's hard in C++.
Right.
And
I mean, if only we had a parsable language, this would solve a lot of problems. But I think that ship has sailed a few decades ago.
And one more thing, let's say we instead of implementing it ourselves at compile time, we have a hook to the parser of the language of the compiler. Then we need to have consistent return result from the parser across all the compilers. So we will need to have standard intermediate representation anyway across all the compilers.
Yeah, so it's a tough nut to crack, for sure.
Yeah. I mean, I think it also goes to, you say Rust-derived macros are token to token, and technically true, But everyone who implements a Rust macro uses the proc2 library,
Mhm.
which parses the tokens into an AST and then lets you output an AST. And
Well, you
that-
output tokens though.
No, you can output like the proc2 library. You have there's a thing to say, great, take this AST and go to a token stream for me. And so everyone almost everyone operates entirely in the AST to AST space, and just has proc2 like tokens to AST to tokens before and after.
Mhm.
And that's what you sort of hear here is people are like, I don't want to parse C++ from tokens. I want a library to do it. But boy, oh boy, I do not want to embed like the entirety of Clang into every thing I have just to use token generation.
Okay, so I took you all kind of on an interesting journey today, I think. So I started out by throwing out that I think we should strive for this guideline, that no raw code, right? That we should try to recognize when we're writing incidental data to our main application and try to automate away the generation of that. But of course, we don't have all the language facilities that we need to do that. And then, even though this is C++ now, you're all here, you want to learn about what's on the cutting edge of C++. And then what I did instead is I spent all this time talking about C, and then I showed you a bunch of Swift and Rust code, which is notably not C++. And hopefully, I think you agree that was a worthwhile journey to take, because I think it's interesting to look at what other languages that are fairly similar to us in a lot of ways, the kind of choices that they made, and what we can learn from them. And I think it's through taking this journey that I think I can make kind of my contribution to how to answer this question, which is, personally right now, I think that this token sequence approach is the most viable path for C++. But ultimately, regardless of the specific details of a lot of what we decide on, I think the fundamental point is that however source code generation ends up looking, it must allow all of C++. I don't want another kind of discovered sublanguage with its own algorithms, with its own domain libraries and stuff like that. I want source code generation to look like C++, in the same way that when I look at these other languages, like source code generation in Rust looks like Rust, except for declarative macros, and source code generation in Swift looks like Swift. And that makes these things a lot easier to learn how to do. Because ultimately right now, reflection is only half the story. And even though we don't really have an answer yet for what the other half ends up looking like, I'm hoping that this at least gives us some more information to think about what it might look like in the future. Thank you. Yep.
I understand where you're going with this, and I think I agree with this, but I want to play devil's advocate and challenge it on one point.
Sure.
If I were to, let's say, okay, I don't have any of this now, I'll solve it by a two-step, like a preprocessor two-step compiler kind of. I'll write a script that goes over, let's say, reads my struct, generates, what's the formatter, printer, serializer. I wouldn't write that script in C++. C++ is a terrible language for writing compilers. So do we really want all of C++? If I don't want to write this, extended C++ to C++ compiler in C++, do I want to write that thing in C++?
Yeah, so I do think we do. And so I think, going back historically a bit, one of the main benefits of class templates over macros is that with macros, you have this problem of, okay, I can have a macro that generates my type, but I need this pre-step of I have a macro to declare my type, and then I have a macro to use my type, right? And so one of the things that class templates allow is that I'm just somewhere in code in a function template, I need a vector of this type, I just go vector t, right? So I don't have how do I go out and inject my type somewhere? There's no real place where an external generator could run and produce the code that I need. Whereas if within the C++ compilation process, because it is very complicated, I can produce types on the fly as I go, and reflection makes it a lot easier to produce a lot more interesting types on the fly. I want these random types that I'm producing on the fly to be formatable. And so where in this process can I make them formatable if not within C++? And so there's certainly like a lot of places where, yeah, sure, like an external code generator could solve the problem just fine. But there's a lot of places like that where I need kind of this core functionality that if it's not within the language, it just adds a lot more like friction and
No, I wasn't
usability.
advocating for external code generation as an ultimate solution. What I was saying was, if I find it a lot easier to use a different language for external code generation because it has much better string handling facilities, wouldn't I run into exact same problem trying to use C++ to require C++, and wouldn't I want for the same more powerful string handling facilities?
Well, so I mean, this is part of why, like, I mean, I don't think that strings are the right answer here, because I think strings have like their own set of problems. But like, I think it's possible to add the facilities that we need to make like sequences of tokens easy enough to handle for a lot of these cases. And then everything else outside of like the literal handling of tokens, like if this is just C++ and I'm just manipulating data structures, well, like, I mean, we have algorithms for that. We have data structures, we have range adapters, and we can keep adding more of those things. And the advantage is that like, we're not even just adding them for this specific problem. These are broadly useful things, and we can broadly use them in more places, is kind of my approach to this problem.
So speaking of string handling, what is it that you see that we need in C++? I mean, you've already got a paper about interpolation of strings. Is there other things beyond that you see I mean, because it doesn't seem to me like there's any fundamental problem with C++ handling strings well. It's just we don't.
Well, like, so, some of the most basic operations for strings. And so, like, I'm not going to talk about UTF because I don't know anything about Unicode and I don't want to know anything about Unicode. But like, when talking about like really basic like string manipulation stuff, is like, how do I split a string? How do I join a string?
Correct.
Like, I showed some Swift code where it's like, okay, I join a string by like typing .join with a separator, and like I don't have to think about it. Like, do we have string.join? Do we have string.split? And like, this is the kind of thing that like, okay, once we start going down this route of like, well, maybe we should have string.split. And it's like, well, what's it going to return? Like, is it going to return like a vector of strings? Like, no, it's like, we don't want it. We want like a lazy whatever. And it's like a lot of the time, especially when I'm doing string stuff, it's usually around configuration for my programs. And like, I don't care if this allocates a vector string. Like, I want the result to do my job because like I need these pieces to go do something else with. And if it takes like 5 milliseconds longer to start up, I don't care because like the performance is irrelevant for me. So just like all this lack of just these convenience facilities. And of course, like, people just write like bespoke libraries. Like, I wonder how many versions of string split that just return a vector of string exist in the wild.
Tons.
Thousands.
Yes.
Right. And so I don't know. That's kind of sounds like existing practice to me.
If you had trim, split, join, you'd have 90%.
Yeah, those are pretty useful. Yeah.
Python has a pretty good enumeration on the string class.
Pattern matching would be the other one. I want to split the string by sequence of patterns and placeholders for everything in between them.
That's the
Yeah.
That's why we need split win in views.
Yeah, lots of languages have much nicer facilities for arbitrary string splitting.
Perl has that like since way back when.
Yeah, I mean those would be nice to have for sure. Yeah, Mark.
Yeah, great talk. We've been thinking a bit about runtime code generation and what the syntax for that would look like, and how it would be very nice if it looked a lot like the syntax for compile time code generation. If you wanted to make those two syntaxes look alike, how would that affect designs for token sequences or whatever?
That's a great. I have no idea. So by runtime code, do you mean like jitting?
Yeah.
Like demos? Yeah. So I have thought about that problem zero. So yeah. I don't know.
Yeah. I mean, right now we just generate strings and it sucks.
I got nothing to offer there yet.
Sorry. Yeah.
Jitting templates, Hal Finkel was doing some work on that, but he's no longer doing it. And we can talk about that later.
All right. Well, thanks everybody.